Oh, looks like we're live right now. I'm just going to update this to this view for a moment. Yeah, so good morning. I don't know who's watching this right now, but if you are, I appreciate it. You're one of the few people. So where am I at right now? Well, yesterday in the afternoon, I finished the final lecture. So now out of the 24 lectures, I've watched all of them at least one time, which is a good first step. This means that I've covered the material. I like to think of learning these kind of classes as having essentially three phases. There's more to it than this, but these are the three phases that I like to consider broadly construed. The first layer is coverage, just getting through the material at least once. Now, there might be more coverage. There might be a second time going through it. There might be, I might go through the textbook for an alternative explanation. I might go through the lecture again if I didn't really understand it, and then now I need to pay attention to something that I didn't catch the first time. So I like to think of the first pass through coverage as being an important milestone, because this is now where, in theory, you should have the underpinnings to be able to do the class. Now, this class is a little unusual, a little different, because there's a more explicit, okay, well, this is going to give you the conceptual understanding, but in terms of the technical skills needed, the way MIT classes are structured, these kinds of classes, is that there are lectures which tend to be more conceptual, more, okay, we're going to go over the high levels of an idea. And then there is recitation, which is kind of like the lab classes in other types of classes. And those lab classes or these recitation classes are more about the technical stuff, more about getting more comfortable with the math. Now, I don't believe we have any recitation things. Let me just double check before I see that I'm not, yeah, I don't see anything for recitation here. So that means that I'm missing sort of some of the actual lectures, you could say, you could call them for the class. Now, the coverage is sort of the first phase. And then the second phase that I like to think about, or second part, because they don't always happen in a linear sequence, is practice, which is actually working through the problems that you're trying to solve. Now, in a class like this means going through the problem sets. It means going through practice exams. It means basically testing yourself on the material. So you understood it in the class. Now, can you apply it in the lectures? And that's not a trivial thing. In particular, I did the first 10 lectures. I was feeling pretty good about those. And then I started doing the first 5 problem sets, and I was feeling not so good. And the reason is just because the math is hard. So even if you have a high level kind of coarse-grained understanding, to be able to translate that into doing math is not always easy. So the practice is probably going to be the majority of what we're doing. So I'm not trying to describe these as evenly spaced phases. So the coverage was this, and then I've got practice, which is going to be a lot. And then at the top, I would call it insight, but I would probably include drills in it as well. But basically, the idea is that you do this sort of bulk practice, which is solving problems, solving specific situations. And then there is a kind of reflective moment where you say to yourself, okay, what are my specific issues that I should handle in isolation, separating them out from this sort of broad doing practice problems, and focus on them in particular. So there's 2 main ways that for a math class like this, that I could consider doing this type of work. One is to do things like the Feynman technique, which is about building a stronger conceptual foundation. And the other would be doing some kind of technical drills, meaning, let's say, I'm not very good at integrating by parts, or I'm not very good at the Taylor, expansion, or I'm getting the chain rule confused, or I still haven't figured out how the Fourier transform is. So I use kind of a combination of those two, but I suggest them up here because basically what this means is that instead of doing a whole problem, you are isolating one piece and working on it, or you are trying to get some kind of conceptual understanding that is not evident to you when you're working through the problem set. And so the Feynman technique often involves doing a little bit of extra coverage. So that's why I said that coverage, you don't always do it one time. So for instance, when I was doing the first 10 lectures, first 5 problem sets, I decided to go back through lectures 8 and 9. Well, almost all of 8 and some of 9 again to really try to understand those methods because they were kind of confusing me a little bit when I was in the class the first time. And that will happen. So there's a chance that I might go through some lectures now because what I was just sort of like, okay, might actually be obscuring some difficulty that I don't see right now. So this is sort of my basic approach to learning these classes. It's not a complicated approach. I don't think that if you were to, watch a sped up version of me doing this, that there would be too much I'm doing that would surprise you, that would be like, that doesn't make any sense to me if you've done any of these kind of classes before. Instead, I think where the efficiency comes from and where the effectiveness comes from is often in making small decisions, making little decisions about how many classes should you do before you start doing problem sets? When you get stuck, how should you handle it? These kinds of little decisions that come into play. And so I try to generalize with these sort of more abstract concepts of coverage, practice, insight, or these kind of ideas. But in reality, a lot of it comes to just sort of this intuition for things that having gone through a lot of these problems. And so I've done now the better part of 5 problem sets. So out of the 10 I've probably done, well, I've finished up to 5, but there was a few problems in the first. There was one problem I think in the first one, 1 or 2 problems in the first one, like 1 or 2 problems in another one, either because I hadn't, you had to watch a big long thing that I didn't want to start watching a big long thing, or there was one that I needed to have Java installed. Still don't have Java installed on this computer, so I'm not going to be doing that one today. And I think there was 2 more in the 5th problem set that I decided to take a break, do some Feynman techniques, but then I didn't go back to them. I just went straight into the lectures going there. So we've got probably 5 full problem sets plus some work on the previous 5. So we've got that material. Given the rate that I've been going through it, I think I could probably get through that in a couple days. So I would be surprised if I'm like, I think I should almost certainly finish all the problem sets next week. And then there's going to be a question of what to do with the remaining, week-ish, 10 days that I have left in the actual class. And that is going to be, that's going to be an issue just because if I run out of material, if I run out of problem sets that have solutions, it's going to be harder to get feedback. So one thing I'm going to be doing and looking at doing is that I have not gone through them in any depth. So I don't really know how good they are. But I do have this textbook, An Introduction to Quantum Physics, and I was just sort of kind of going through these, and I recognized that, oh, wow, they actually have solutions at the back of this book to exercises in the text. Now, I have not read most of this text. I just looked at some sections. So there's some issues possibly here that this may cover different material. The problem sets might be quite different than this. So I don't want to say that I want to rely on this. Definitely not going through it blank. But if it does turn out that there's some areas that I don't feel as confident in, like I was struggling with these kinds of problems, if I can find analogs to those problems in here, I might be able to work through them as well. And because presumably the problems are explained, the fact that it's not from this class isn't going to be as important. That's more important when you're taking just an evaluation method from a class, but you don't have the material that they used. So sometimes there's differences in notation, differences in what they expect you to learn, what they expect to focus on, and that can create problems. I don't know how big they are. They're not usually that big in physics, which tends to teach things exactly the same way. Whereas when I found for like biology and chemistry, when I took those classes at MIT, there was considerable choice about what you could do and what you could cover. And so therefore, there was like whole units from chemistry that varied from class to class. And if you hadn't taken that unit, there's no way you can answer it on an exam or something, for instance. So I think we're in a pretty good spot right now. I am a little bit ahead of my goal. My goal was to finish all the lectures by the 15th. Although given that the problem sets are harder than I was anticipating, I shouldn't feel too confident about that. Doing the lectures is easy. You can always do the lectures. They don't require feedback, so it's mostly just sitting in the chair and listening. Obviously, if the lectures are really hard, you're not going to get as much benefit from listening to them if you don't understand what they're saying. But in the same sense, watching a bunch of lectures is not that difficult a task. It's going to be solving the problems, working through it that's challenging. So I think what I want to do now is go through the rest of the problem sets like I did at the very first thing I did when I started this class was I went through problem sets 1 through 4 just to kind of get a sense of what's being covered. Now, I didn't do this before the lectures this time. There's no real big reason for that. I think I just decided to move on to the lectures and go through them. But I think what I want to do is read through that problem sets now and just get a kind of sense of high level, do I feel like I know how to do this? It's going to take a little bit of work to get there, and I might need feedback, but it would be good to kind of get a sense of, I don't understand this at all. I kind of understand the method, but I don't really know how I would calculate it, or, oh yeah, I know the answer to this, or I could confidently arrive at the answer with a little bit of mathematical work. So I'm just going to shift over now, and you know what, I'm just going to grab a little bit of water, and then I'll be right back. Now, I'm not entirely sure why the lighting for this camera sometimes goes a little blue. I think the automatic white color balance for this is not as great. So I'm going to lower the lights just a little bit because I find that kind of annoying on camera that it looks like I'm writing on a blue paper or something. So I've got some pencils here, freshly sharpened, and let's open up the you know what I'm going to do? I'm going to switch to this view. All right, and let me just make sure it's the right size. It can be a little wider. Okay. Yeah, this looks pretty good. So I think I'm just going to, the downloading is pretty fine. So I think it's been a problem here. So let's just look again at what our materials are. I've almost forgotten all the materials. So we've got our assignments here, which from their website has these 5 problem sets. So I've kind of done the better part of these 5 problem sets, and I've got another 5, and we have solutions for it. We have exams, no solutions. So these might be useful if I can get to a point where I'm able to confidently answer all of them. I don't like doing exams that have this much calculation without having solution sets, just because it's so easy to make trivial mistakes. Like you put an H bar, you know, instead of H bar, you have 2 H bar or something like that. And so it's very difficult to, without knowing the solution, it's very easy to make mistakes, and that's what you want the feedback for. So we've got that. What do we have here in study materials? Yeah, these are just different. So this is Mathematica. I have not downloaded Mathematica on this, but we might use it to just understand some things here. We've got a few recitation notes, some additional notes, and then a little bit of resources here. Janendra, I think that's Janendra, I'm not sure if I'm saying your name right, is saying, asking if I plan to do data science. I might like to do data science. Honestly, I might like to do something with machine learning. I haven't decided how I want to formulate a project like that, because this one here, this month-long project was just intended to be kind of a small project that was a format I understood well enough. Not to say it's easy, but I understood the format well enough that I wouldn't be too concerned about how to go through it live on camera. So I know how doing an MIT class works. I did quite a few of them, so I felt like it would not be too bad. Whereas machine learning, I don't really want to just do more MIT classes. I already did some MIT classes for machine learning. So if I was going to do data science, I want to do something practical, but I haven't really decided what I would be doing if I were doing it practically. In any case, I wouldn't be doing it for a little while. This was brief month that I had where I didn't have too much other work to do, so I could get away with working on this little project. We have readings here. So these are all the textbooks I don't have, but I might be able to, yeah, nothing really here. Let's see what we have. Lecture notes. I don't think we have all of them. Yeah, we only go up to lecture number 8, which is unfortunate because I would have liked to have seen a lot of things here. But I mean, a quantum harmonic oscillator. Yeah, this might have been useful. I kind of already went over this. So I don't know whether it's super useful. What else do we have here? I think that's all we have for right on this course. Let me just look and see what we have for the other sessions, just because physics, where is physics? Here we go. So I just want to just double check what we have for the other sessions. So we have quantum physics. So we just have 2 sessions on OCW. So this is Barton Zwieback. We also, I think, have video lectures here. Oh, this is a little bit different. I think this was for MIT edX, so that's why they're not the normal thing. But I can keep this in mind because this might be useful if we're trying to understand something. Let's just see how far it goes. Levinson's theorem. Like, see, some of this stuff is different. See this Ramsauer-Townsend effect. I don't know. I don't remember hearing those names. Okay, let's see what they have. I think, do they have any assignments here? So we have assignments, problem sets, pretty confident these have no solutions. This looks almost the same as what we had before. Yeah, this is exactly the same problem sets, I think. Let me just double check. Do I recognize these as? They look a little different. Okay, these are different, but yeah, I mean, for some of the ones, for some of these that just say show X or something, or that they have a kind of self-evidently, like, you know, when you've got the right answer, I might be able to use them, but otherwise not. And then we've got, yeah, final exam here. This is again without solutions. So let me just double check. I don't think there's any solutions on this. I mean, it'll be useful for just getting a sense. I can still work through them to get a sense of how the exam works and stuff. All right. From a previous term, so it's not even from this term. All right. What else do we have? Is there any course materials? It's just the whole thing. Do they suggest this book here? I thought this is French and Taylor. Do I have French and Taylor here? All right, where is okay, so I don't think we have any more material here. Let me just check what we have on Stellar. I just kind of want to do a little review of what materials I have, just so that I'm not, you know, thinking I have something that I don't really. So let's just do 804. So this 804, this is so basically Stellar is MIT. So MIT OpenCourseware is intended for everyone. Stellar is intended for MIT students. So it's not really intended to be public. However, if you see here on the access side, there will be MIT, meaning that anyone from MIT can access that. Class, meaning that you have to be a member of that class to access it. And then there is public. Now you can see there's very few public ones, but there are some. I think I did get to one that was public. So let me just go here. No. Here we go. So we got one public, one fall 2010. I think this is the only one, but I'll just double check. Oh, fall 2012. Okay, there's two here. Maybe it was just one of them had an exam. So I use this a lot during the MIT challenge when I didn't have, if let's say a class didn't have final exams, I would check Stellar because sometimes Stellar had final exams. So this one here, see if we have any problem sets with solutions. Oh no, it's giving me a hassle about this. Is this one public? Okay, so we have exams here, but I don't think these have solutions. Yeah, I don't know solutions there. Okay, but good to know. There is some exams in case I want them. I don't think, yeah, problem sets giving me an issue. Lecture notes. Okay, we do have some lecture notes. I don't know how useful these will be. Let me just see what they look like. Must be handwritten. They're taking a little while to download. Materials, what do we have here? Problem set 1. Well, why is this not loading when I tried to load it? Yeah, it's locked. Okay. All right. This is not going to be terribly useful, I don't think. Oh, here we go. We do have exam solutions. This is good. Okay. Yeah, practice final solutions. Oh, these are the ones. Yeah, this is definitely the ones that I remember here. So this final exam. So we have practice final solutions, final exam solutions. But I don't think they have the final exam here. So I don't think that there is. So I can use this material. You know what? I'm going to take these practice exams 1 and 2. And I'm just going to save them right now. All right, let's go to save it in my 2006 version. Yeah, I'll just, I'm just going to dump them here. Oh, this is the same thing. Okay, let me just save this here. All right. And then we have, I already downloaded the, oh, there's 3 documents for this, great. So let me just save these quickly. I'm not going to look at them, but this will be good because then we have another. I'm a little bit nervous about not having enough feedback material. So never hurts to it's always a good sign when the exam has corrections to the solutions. There was a mistake in them. All right. Exam 2 solutions. I don't think that, no, doesn't matter because these are the actual exams, and I don't think that the exams were present here. So I don't think I actually have these. So I think these are the ones that I have. I downloaded that final, so I did see this one when I was doing my first search of the material here. So I have this textbook, French Taylor. Do they have readings here? Because it would be nice to see how the readings match up. Practice midterm exam solution. So this, I'm assuming, corresponds with this. Are these the same? I think so, yeah. All right, let me save it. Save pages. So we may not have finals, but we do have more midterms, which is nice. Textbook problems and homework 5, homeworks. Can I access these? No. All right, that's unfortunate. What is it saying here? Yeah, it's not letting me access that. Let me check their calendar here. Yeah, this is just homeworks. And you know what? I'm going to just do a quick Google search for Google. I forgot I'm using Chrome. OCW. I'm just going to do 804. I was already looking for these things. So we got this. This is YouTube. This is, yeah, I already have this one. Oh, this is interesting. What's this here? Oh, no. Don't want to go that far. Course home. Spring 2006. Oh, wow, this is super old. So what do we have here? Oh, we lucked out. So there's no final exam here, but we have another 2. So this is why I take my time and do these searches, because sometimes you can find these goodies. So we only have midterms here again. So I prefer finals to midterms because they're comprehensive, but I will settle for midterms as well. And let's just see what the, do they have anything for readings here? Oh, good. Okay, so they have French and Taylor here. So I'm gonna just save this page too, because this has, so what did we do here? We've got Compton scattering. So we didn't do Compton scattering. Oh boy. So I think this is similar. There's a few names to references to names that I'm not as familiar with here. But you know what I'm going to do? I'm just going to save this page here. Where do I? Oh, I'm not used to Chrome here. How do I do the save as PDF? And then let's just go back and put this in. Let's put this. You know, I'm going to make a new folder. Just like readings here. Oh. Let's just drop that there. Okay. So this is an example of like, I can't even find this class with the regular OpenCourseWare search. So it's like an older class has been like replaced. Let's see what they have. We've got the example, check those. Problem sets, I don't think these have solutions. No. Doesn't look like it. Okay. Lecture notes. I mean, could be useful here. Let me see what they look like. They're just handwritten. Oh, it's not so bad. Okay, maybe useful. I don't know whether I necessarily need more notes though. Okay, we've got this. No assignments. All right. Okay, I think, yeah, I feel like this is, yeah. All right. I think that's all we can get from this. There's no videos or lectures or anything like this. Let me double check. I don't understand how this is a Faisal thing. I'm not sure what this is. Physics. Let's see if there's any more 804. Yeah, spring 2006. That's it for here. Okay. Okay, let's see if we have anything else here. What do I have in Course Hero? Fall 2013. I'm not sure what this is. No. Probably going to run out here. Physics forums, okay. Do we have any notes here? No. What is this one here? This is spring 2013. So this is, yeah, where I already have this one. Spring 2013. What do we have here? Already have that. All right, I think that's probably good for now. Let me just go back to our main course page here. So, yeah, so this is, I think we're ready to get going now on the problem sets. We found another set of practice exams, although it's from like, I think it was from 2006. So this was 2013, which means that there would have been how many years separating that? There would have been another 7 years in between. So there's a possibility that they're not covering the exact same thing. Yeah, I think we're pretty good here. I'm just also close some of these pages. Now I would say, yeah, probably what I want to do is just go through the problem sets I have and then look at what do I want to do with those and get started. I know this was a little bit of a detour this morning. I'm not really doing much learning, just finding materials, but having materials helps a lot. So I usually try to, especially a class like this where I want to make sure I have enough materials. So let's go through the assignments now and just read through them. So I'm just going to write this down here. Previewing. So just get a sense of what kind of questions we'd have to do. Exam corrections, geez. All right. Oh, this is, I guess, yeah. Well, I have not done that, so I can't ask that. Finding meaning in the phase of the wave function. Suppose psi naught of x is a properly normalized wave function with the expectation value of the position operator equal to x0 and the expectation value of the momentum operator at p naught, where x naught and p naught are constants. Define a new wave function, psi nu x is equal to e to the I qx over h bar psi naught of x, where q is a real number with the appropriate dimensions. What is the expectation value of x nu in the state given by psi nu? What is the expectation value of the momentum given by this? And based on your results, interpret in one sentence the physical significance of adding an overall factor of e to the I qx h to the wave bar. So I would want to work through this a little bit here, but I'm pretty confident that when you add e to, like, this is a pure phase. This is e to the I q. So this is going to, I want to say it's going to boost the, so this is like a boost by q operator. So this should increase the momentum by q, but not change the expectation value of the position for this new wave function. So I feel that's pretty good. Relation between wave function phase and probability current. So question 3, consider a particle with mass m in the state described by the wave function psi of x. You can always express the wave function in amplitude phase form as psi of x is equal to a of x e to the phi with some x dependence, where ax and psi x are real functions. Show that the probability current is given by this fancy J is equal to the amplitude squared, h bar over m, the partial derivative in x of psi of x, i.e. the probability current is proportional to the gradient of the phase. Okay, that doesn't seem trivially true to me, but I think that I could probably do that with some math. Show that there can be no current in a region where the wave function is real. Interesting. I'm assuming that the logic behind this is that the way that we're having momentum is through these phase terms, and so if there's no movement, there's no probability current. I think there's something related to that, although obviously momentum is the whole thing, so maybe that's not the right way to think about it. How large is the current for a plane wave of wave vector k? Good question. My guess is it would be the gradient of that phase. I would say k. It would be proportional to this k, right? Because we're going to have e to the I kx for this plane wave. That's the whole thing. The amplitude is 1, so that's 1. H bar over m. So it'd be h bar over m k, no? K just drops down there. That'd be my guess. Calculate the current in a region where the wave function is given by b to the e constant b, e to the alpha x, plus alpha x, and c e to the negative alpha x, where a is a real constant and b and c are complex numbers. I, b, c are not position dependent. Is it correct to say that since these are real functions, the current inside the barrier must be 0? Find a condition on b and c such that the current vanishes. So this is related, obviously, to the idea that when we have the classically disallowed region in these harmonic oscillators, so you've got a part in the middle where you've got the thing moving, and it has this sort of imaginary component that's doing this, and then outside of it, it's real, and those are real exponentials, which means they taper off very quickly. And that tapering off means that there's nothing going into them because they're trailing down to nothing, whereas these ones are oscillating so that the current would actually be moving. I think that's what that means. So I think this is pretty straightforward. 4, odd parity energy eigenstates in the finite square well. Consider the finite square well potential of depth v naught and width 2L. V of x is equal to negative v naught, x is less than L, 0 else, where v naught and L are real positive constants. So we're looking at here, right? In this odd parity bound states. The width L sets a characteristic length scale for our finite well, using dimensional analysis to identify a second characteristic length scale, R naught, and a dimensionless measure of the overall size of the well, G naught. Give a physical interpretation to R naught. So this is going to be dimensional analysis to try to find the characteristic width of the ground state, I'm guessing, of the finite well. That'd be my guess. Derive a transcendental equation for the allowed energies and solve it graphically. I think that's what we did in the class, where we had to, you've got, it's some horrible tangent function, but basically we have to get the matching conditions so that the sides match. So you have to get those exponentials have to go down at exactly the right rate to hit the 0 at the same time as you've got the sine function. They have to exactly cancel out, and that's what's the transcendental equation. Examine the two limiting cases of a wide, deep well. G naught is much greater than 1. And a shallow, narrow well. G naught much less than 1. Describe the character of the solutions in each limit. So this right now tells me that this V naught we're having here is going to play a role in this R naught. How deep is the well, you know? Is there always at least one odd bound state? If not, what is the condition on G naught such that an odd bound state exists? Well, an odd bound state would be having one node, which I don't believe would be generally true because you need to have a ground state that's even, but you don't need to have a first excited state, which is odd. So my guess is that it has to be shallow enough that you'll only have the ground state and not the first excited state. That would be my guess. Explore the dependence of the energy eigenstates on L and V naught by playing with the one well part. Let's see if this looks. Oh, I think. Oh, yeah. I think I need to have. Yeah, this is. All right. All right. So I need Java for this. Got to put on my to-do list. You know, I'm gonna put on my to-do list right now to get Java because this is. It's bad that I don't have it right now, and there's a lot of things that need it. Okay. Question 5, quantum glue. Consider a one-dimensional system described by a particle of mass m in the presence of a pair of delta function wells of strength W naught greater than 0 located at x equals plus or minus L, i.e. V of x is equal to negative W naught delta x plus L minus W naught delta x minus L. This is a rough but illuminated toy model of an electron in the presence of two positive charges located x equals plus or minus L. Delta function wells. Interesting. Okay. So normally we had this step well, whereas now we're just seeing like two wells, like it's up, down, and then up again. Derive a transcendental equation for the allowed eigenenergies of any bound states. Express the result in terms of the dimensionless quantities G naught and this, where this is the negative energy of the bound state. I think the idea is that when we have a delta equation, we should have exactly one bound state because the bound state never goes away. But now we have two of them. So there's probably going to be an interaction, I guess, depending on how far apart they are for that bound state. Solve your transcendental equations graphically / numerically to identify all bound state energy eigenvalues. How many bound states exist? Does the number depend on G naught? Okay. Well, this is going to be a hint for this G naught up here, isn't it? C, plot all bound state energy eigenfunctions for G naught equals 0.1, G naught equals 1/2, and G naught equals 10. So I guess you'd have more than one bound state. My guess would be that you'd only have one bound state when you're dealing with this showing up, all right? Yeah, I'm going to just scooch my windows over here just so that they're not... just so that we're not... you know what, I'm going to just slide this guy over a little bit. How do I slide it over? Just going to adjust my window just briefly so that I can... let me just shrink this. I just want to try to maximize the screen space of this thing. Okay, I think this is good enough. All right, let's go back. How does the energy of the most tightly balanced state vary? So I guess you have more than one balanced state. I guess because there's the second well, so you'd have to, right? But I don't know. The way this is saying it makes it like thinking delta function, you're just going to have the one balanced state, but now you have two wells, so maybe that's why. Shows the energy as a function of L. No, you do not have to edit that likely. Well, you gotta have two balanced states, I guess, at the very least, right? Because they're going to be so physically separate if the L goes up really large. So my guess is that you would have two. This, maybe superposition of both. I don't understand why you're going to have more than two here. Using Mathematica. So I should probably get Mathematica, I guess. I don't know. I'm not going to really work with the Mathematica ones right now because I don't want to have to get into learning that at this stage. E, suppose we place the particle in the lowest energy bound state. Do the two delta functions want to be close together or far apart? Plot the induced force between the delta functions as a function of L. Interesting. Use the above to suggest a plausible explanation for why hydrogen is a stable molecule. Induced force. Like, I'm not sure how I'm going to do that. But explore so use this quantum balanced state applet to explore the dependence. So I need to get Java again. Dependence of energies on of the various bound states of a pair of identical wells as a function of the distance between the wells and the shape of the wells themselves. How does the splitting between levels change as you increase the separation between the wells? Why does the second excited state have the same number of nodes inside each well as the third excited state, but not the same as the fourth? So we've got multiple excited states here. I thought there was only one bound state inside of a well, a delta well. But maybe it just depends on this. Maybe it doesn't depend on, well, anyways. All right. Further facts about Hermitian operators and commutators. Recall that the Hermitian adjoint of an operator, A hat, is defined as the operator A hat dagger, such that for all functions f and g, f inner product with A hat g is equal to A hat f inner product with g. Show that this is equal to, all right, so these are some simple. Okay, so this is just some math. I gotta show some of these proofs right here. Recall that an operator is Hermitian if it is equal to its own adjoint. So A dagger is equal to A. Henceforth, let A and B be Hermitian operators. Define C as the commutator of A and B. Show that the adjoint of the commutator is negative. Such an operator is called anti-Hermitian. Show that the eigenvalues of the Hermitian operator A and B are all real. So I think the idea here is we're trying to show that the Hermitian operators correspond to the observables. So X hat, P hat, E hat, these are Hermitian operators. Anti-Hermitian operator are all imaginary. if that were true of this anti-Hermitian operator is all imaginary, then that would mean, I guess we haven't seen, when we've seen the commutation relationship, like it's I, what is it, IH bar or 2, what is it, an X and it's IH bar, X and P, so that's imaginary. All right, suppose K and J is equal to minus Sj. All right, this is a real quantity and K is Hermitian. Is J Hermitian? Show that Kj is equal to plus Sj. Okay, suppose K psi K, K psi K. So this is K is the eigenvalue of this state. Oh, excuse me. Show that Jk is an eigenfunction of k hat with eigenvalue k minus s. Okay, these are, I think I can figure these out. These are just simple math right here. In the harmonic oscillator, what operators play the role of k, s, and k, j, and j dagger? Well, because we got a plus and a minus s here, this is almost certainly going to be the annihilation or the lowering and raising operators. And then this would be the energy. And just tell that at a glance. Side Y Hermitian. Yeah, let's just read this. So, okay, so there's only 6 problems here. So that's all the problems for problem set 6. Taking it as a postulate that observables in quantum mechanics are represented by Hermitian operators with the observable values determined by the spectrum of eigenvalues of the operator. We've justified the restriction to Hermitian operators by requiring all observables to be real. However, it is easy to construct matrices which have all real eigenvalues, but which are not real. For example, consider the matrix, anyone at this I. M's eigenvalues are both real, but M is explicitly not Hermitian. So clearly reality of the eigenvalues is not enough. What gives? In fact, we need one more requirement. Observable operators must admit a basis of orthonormal eigenvectors in order for the rest of the rules of quantum mechanics to make sense. See why? Consider again our operator M hat. By construction, both the eigenvalues are real and non-degenerate. However, the corresponding eigenvectors are not orthogonal. Okay. As you can easily check. Now consider the consequences. If I tell you that a sample system in my lab is observed to have m plus 1, you say, cool, by the rules of quantum mechanics, I can observe this with coefficient. If I then ask you whether a subsequent dimension might give m equals minus 1, you're obliged to reply, if the eigenvectors are not orthogonal, you can't even be sure of the thing you just measured. That is bad. I might look at this again after I go over this little thing. I think would benefit from reading after I do all this work on the Hermitian. Okay, problem 6 doesn't seem that bad. It doesn't seem that bad. Problem set 7. Facts about unitary operators. So this is more stuff on unitaries. Unitary operator whose adjoint is its inverse. A U dagger U is equal to the identity operator is equal to U dagger. Show that all eigenvalues of unitary operator are pure phases. Can an operator be both Hermitian and unitary? My guess is no, because Hermitian implies real eigenvalues, and these are not real. But maybe if there's plus or minus 1. I guess they could be both Hermitian unitary if they were plus or minus 1. All right. Suppose M is a Hermitian operator, so that EVIM is a unitary operator. Show that the product of two unitary operators is also unitary. Suppose U is a unitary operator and V is state. Show that by acting on V with U preserves the norm of V. So I mean, unitary operator is it doesn't scale. It's like they they're not scaling. We're only adjusting things by phases. Call their old friend, translate by L operator, which shifts the expectation of value. The position by L, boost by Q. Verify that TL and B are both unitary operators. Okay. 2. Quantum evolution is unitary. The time evolution of a quantum state is dictated by the Schrodinger equation, IH bar. Time derivative of psi of xt is equal to, okay, blah, 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 where E hat is the energy operator. The meaning of the Schrodinger equation is this. Given the state psi x 0 at some moment in time t equals 0, given the operator energy, we can unambiguously determine the state at any later moment in time by directly integrating this differential equation. And thus define an operator U hat, which maps any wave function at time 0 to its Schrodinger evolved form at time t. Give a physical reason why this must be unitary. Well, it's because we want to conserve probability. Give a physical reason why UT must satisfy a simple composition law. Well, this would take it psi 0 to psi t. So we take it to T1 and then we take it to T2. It should be the same as we take it to this. Yeah, okay. Use a Schrodinger equation to show that U hat T satisfies the operator equation. Time derivative UT is equal to negative I over H bar E energy operator, UT operator. I guess basically this is saying that if you took some wave function psi and you applied a unitary operator to it, that the resultant wave function should also obey the Schrodinger equation same way. Find the most general solution to this differential equation which satisfies the above two properties. Which two properties? These two? Do we have a form of UT? UT is often called the evolution operator, the propagator. In principle, we can always solve the Schrodinger equation by simple exponentiating, acting with the resulting UT on a given wave function and evolving. Exponentiating an operator is generally not a trivial thing to do. Nonetheless, we can often learn a lot about a system by studying the propagator's properties. As an example, identify UT for the harmonic oscillator in terms of N. Ooh, I don't remember what the operator N is. Is this just some generic operator? Or is this something specific to the harmonic oscillator? I don't remember an N operator. I guess N operator here is just the N operator, I think, is just the number, like the state, like which energy level you're at. But I haven't seen it expressed as an operator before, so right. A little more challenging. Oh, an aside. I like these asides. You know, I'm gonna just read the asides when I get to that level in the problem because I think they'll make more sense once you go through the problem. That's how it felt in the first 5 problems. 3, getting a sense for T. 3a, consider the scattering of particles of mass m off a step of height v0. Okay, so I should probably be writing these things down. I'm just doing it with my hands and gestures right now. But so this is just step compute t little tr. So this is the transmission amplitude, reflection amplitude, transmission probability, reflection probability for both energy greater than V0, energy less than V0. So we kind of did this one in the class sketch, this transmission amplitude. How do your results differ when you scatter uphill versus downhill? I believe the answer is that they don't matter, which is very surprising because that's not at all how it is in the real life. Your chance of reflecting off of a downhill slope is 0 in real life. But that's the fact that we have waves. All right. B, in lecture, we derived the transmission probability T for a particle of mass M incident on a barrier of width L and height V naught. For E less than T naught, T was given by this equation. Okay. Was given by that. K squared is measured the equation there. Sketch T as a function of this for very wide barrier, medium barrier, and thin barrier. What is the limit of the transmission probability as the energy approaches the height barrier in each case? Okay, I'm going to have to do some math to solve this, but basically wider barriers are going to have much lower transmission. Then that's just sort of natural. So as T gets, well, I guess we're thinking of energy is less than V naught, yeah. Because that makes sense. If you have a very wide barrier, it's much harder to throw things through them. Very thin barrier, the wave can sometimes ripple through, it can tunnel out on the other side. C, for a high, wide barrier, i.e. G naught much greater than 1, how does T vary with L when E is less than V naught? Comment on the probability of a goldfish tunneling through the wall of its bowl. All right, well, that's pretty unlikely, but that's also because the wavelength is pretty small and the barrier is pretty wide. As we saw in lecture, the transmission probability for a particle of mass m incident on a potential well of depth negative V naught is given by this whole jazz, where K2 squared is equal to 2m over h by the book. All right. So this is the opposite. Now we're going over a well as opposed to a barrier. Show that you can derive this result from that of the barrier of the height plus V naught by taking V naught negative and keeping track of the resulting size. All right, I'm going to have to work through these right now. All right. A hypothetical experimentalist friend of mine is conducting an experiment with a particularly interesting piece of wire, which has a curious localized feature halfway along its length. Decides to measure TE, the transmission amplitude. She reports the following data. Uses data to come up with a numerically reasonable model potential describing the localized feature on the wire. Okay. So this is basically that knowing the transmission and scattering, or transmission and reflection, I guess you just need one because they add up to 1. Knowing the transmission probability, we can uniquely specify the potential that sits in the center there. Properties of the S matrix, scattering matrix. Consider a localized potential, Vx, which vanishes outside of some region. So finite square well, the function, a delta function barrier, etc. Outside this interaction region, the potential is constant. So the energy eigenstates are simple plane waves. Okay. All right, so this is something we've already kind of discussed in the lecture. Scattering is the process of sending particles from far away, watching them swing back, just getting to find it well, a delta function, manticore. Oh boy, physicists. Explicitly by sending in a known set of waves from far away with amplitude A from the left and D from the right, and observing outgoing waves leaving in the direction with scattered amplitudes B and C, we can infer the relations between A, B, C, and D imposed by the potential, and thus infer the physics of the potential itself. A convenient way to encode these relations is via the scattering matrix, or S matrix, which relates the incoming and outgoing waves of fixed energy E in our 1D localized potentials and ingoing waves. Note that we suppress the E dependence on the components of SE. Keep in mind, however, these are non-trivial functions. The energy E, as we'll see, the detailed E depends on components and codes all the physics of the system. Well, this is just basically the same thing as this right here, just doing it in a matrix. As we'll see, the detailed energy dependence of these components encodes all the physics of the system. Give a physical interpretation for this reflection amplitude squared, blah, 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 in terms of observable quantities. I want to say that this is... Oh, I'm not sure that the complex conjugate matters here. Trivially, I'm thinking this is R and this is T and this is R and this is T. But does this complex conjugate matter? I don't know. I'd have to actually do the math. Okay. Design an experiment which measures T. Design another experiment which measures the phase of T. Okay. Physically, why must the S matrix be a unitary matrix? Because we don't lose particles. Use the unitarity of S to show that this is equal to 1, this is equal to 1, it's equal to 0. Columns of the S matrix are thus orthogonal unit vectors. Physically, why must this be true? Well, again, because we don't want to lose stuff. So the columns, these are our vectors because it's B times this is. Yeah, I think it's just to show that we're not losing any stuff. Show that parity, symmetry of Vx under x to the negative x implies that T equals this and R equals this, i.e. that scattering is identical whether from left to right. Oh, okay. So these are not, these ones quantities here refer to the transmission probabilities in a particular direction or in another direction. And as long as it is symmetric, it should be the same. Although we did know from the step function, which is not symmetric, that we have that property. Although this is a little bit of a different scattering situation because the step function, you've actually raised or lowered the voltage across the whole set of situations here. Whereas if we're looking at it this way, I mean, I guess if it was shaped like this, you might get a different thing on each side. The scattering phase psi is defined as the phase of the transmission amplitude. Okay. Show that for any symmetric potential, we must have this being the imaginary component of this. It doesn't seem trivially true to me, but I could probably show that. Discuss the physical meaning of the scattering phase psi and illustrate this interpretation in terms of your experiments in part A. Okay. 5. Scattering off an attractive delta function. Well, consider the scattering of particles of mass m off an attractive delta function potential of strength V naught located at the origin. Meaning that this is a well. I don't know why it's attractive. What does that mean? V naught greater than 0. Okay. Suppose a beam of particles is incident from the left with typical energy E. Calculate the fraction of particles in the incident beam that are reflected by this potential. Okay. Compute the S matrix. Find the scattering phase psi. So that S has a pole at an imaginary value of K corresponding to a negative value of E. Show that the corresponding energy is none other than the energy of the sole bound state of this potential. Oh, so here we are also, this is the idea that was mentioned in the class, that by knowing the scattering matrix, if we take the scattering matrix and we assume negative energy, Well, now negative energy, we're going to have the matrix itself is going to blow up. And we're going to look for poles basically where basically these poles are the only spots where the blowing up cancels, I guess. And so because the blowing up cancels, and this is kind of the matrix equivalent of what we were doing with the harmonic oscillator, that everything blows up on the sides unless you get exactly the right energy levels, which is why these bound states are discrete. And this is sort of the matrix equivalent of it, that we're finding these poles where things, where basically you have a divide by zero at the top. Or at the bottom, sorry, you're dividing by zero, and so at a particular value of k, so a particular energy, and this is the bound system. Explain heuristically why this last result must be true. Why must S diverge precisely the energy of every bound state of a potential? Well, this is because so there's. I'd have to think through this a little bit more. Why this would be. Why this must be true. Now consider a potential made up of two delta functions. Okay. Where again V naught is where V naught is again positive. Compute the S matrix. Find the bound states for the S matrix. I think I can just use Wolfram Alpha for this. I know it's like saying using Mathematica, but Wolfram Alpha will also do it for me, I think. All right. We finished. This is problem set 7. Well, reviewing problem set 7. Let's review problem set 8. 7. Problem set 8. Question 1, superposition state of a free particle in 3D. At time equals 0, a free particle in 3D. Okay. Is in the superposition state. Are we what coordinate system are we in? Looks like it's X, Y, and Z. Okay. If the energy of the particle is measured at T0, what value is found? This isn't obvious to me. Is this some sort of spherical harmonic? Is that what we're looking at? Like, is this an eigenstate? We've got, there's no I here though. I'm not sure. Okay. What possible values of the momentum will measurement find at t equals 0? What probabilities will these values occur? Given the state, what is the state R at t? Well, we know by time evolution that it's going to turn it into this state. Okay. This is going to be challenging, I think. I'm looking at it right now. Okay. 2, degeneracy. Suppose a system has some symmetry, example, rotational symmetry. This means the energy doesn't change upon acting with the symmetry. Example, if you rotate the system. This generally implies that the set of energy eigenvalues is degenerate. Either there are multiple independent eigenstates sharing the same energy. Generosity of the system at some energy refers to the number of energy eigenstates which share that energy eigenvalue. Consider a free particle in 1D with definite energy. How many linearly independent states share this energy? Infinite? I don't know. Oh, in 1D. 2? I think there's 2 because there's one going this way and one going this way. What system guarantees this degeneracy? Symmetry between left and right? Or like, okay. Consider a 2D harmonic oscillator with frequencies omega x, omega y equals omega. A 2D harmonic. What are the energy eigenvalues? Do we have to solve the SHO in 2D here? Seems like a simple question, so I'm assuming that they're going to have the same. We can just do this kind of same node theorem, this 1/2 omega, this whatever. What are the energy eigenvalues? What is the degeneracy of the nth eigenvalue? What symmetry guarantees this degeneracy? Now, suppose we nudge the system so that it doesn't exist equal to. Oh, this is saying it's symmetrical. So we're looking down on it. It's symmetrical. What are the new energy eigenvalues? Is the spectrum again degenerate? No. Plot the first 6 eigenenergies as a function of E for epsilon. Okay. What is the relationship between the breaking of symmetry and the splitting of degeneracies? It means the same thing. All right. Question 3. Angular momentum operators. In classical mechanics, the angular momentum L is equal to R cross P. So position cross momentum vectors is conserved in any rotationally symmetric system. Quantum mechanics, the angular momenta are given by the operators Lx, Ly, Lz. Using the basic commutator relations, show that. Okay, that should be pretty simple. Consider the operator L squared is equal to this. Results above show that this commutes with this one, again without further calculation. All right, that's pretty easy. Consider the ladder operators. Using the above commutation relations, show that this is equal to h bar this. What properties of the eigenvalues of L and this follow from these commutators? That the angular momentum is discrete. Same as we had the simple harmonic oscillator. Where's the one here? Oh, here. It matters because operators do not have the same eigenvectors. Mathematical preliminaries, eigenfunctions of total angular momentum squared and Lz. In the previous problems, we exploited the commutation relations amongst the coordinates and their momenta to determine the commutation relations among the components of the angular momentum. In this problem, we'll use the explicit coordinate representations of the angular momenta in spherical coordinates. Oh God, this is so annoying. It's been not rendering all the symbols. Yeah. Don't worry, I'm not worried how many people are watching me. I'm actually kind of surprised that anyone's watching me. This is more for posterity, just so that I can kind of use this to sort of illustrate my process than necessarily to be entertaining live on camera. So Eee. This is so annoying. Some of these problems, I don't know whether it's Chrome or whether there's a problem with the latex, but like, I don't know what that vector is supposed to be. In spherical coordinates to study the eigenfunctions. Okay. Show that these functions are properly normalized and orthogonal to one another. Show that these functions are eigenfunctions of both this. Okay. Construct that. I think this is basically what we did in the case where you had like the 0, 1 was a ball, and then the like the one state was like this, and then there was the disk inside. So this is the one from Mathematica that we were doing that. All right, next. Angular momenta and uncertainty. Commutator relations you derived in problem 3 above imply an important set of uncertainty relations amongst the angular momenta. Obviously, consider a particle in a normalized eigenstate of L squared Lz. Okay. Okay. So this is just doing some uncertainty, calculating this variance. And can the uncertainty in any two components of L ever vanish simultaneously? No. No, it can't. 6. Lifting the degeneracy of the quantum rigid rotor. Okay, consider a spherically symmetric rigid rotor with a moment of inertia Ix equals Iy equals Iz equals I. For example, it might help to imagine Professor Evans curled into a compact and uniform sphere and set spinning. Classically, his energy is derived by this. Okay. What are the energy eigenstates and eigenvalues for this quantum rigid rotor? What is the degeneracy of the nth energy eigenvalue? Now suppose Prof. Evans gets sore and stretches a bit such that his moment of inertia in the z direction becomes this, the other two moments unchanged. What are the new energy eigenstates and eigenvalues? Sketch the spectrum of energy eigenvalues as a function of. This one's hard. I don't quite know what to think. I think maybe I need to go back to classical mechanics and just review moment of inertia. Moment of inertia was just kind of like, it was some measure of how much mass was distributed over it, so how much things were spinning. So yeah, I have to get a better picture of what's going on here. I think the idea is that we had a sphere before, and now we've got something like this. And so that's going to change. It's going to change the eigenvalues and eigenstates for this system, because before you were like considered a sphere, and so all directions of rotation are the same, and now they are not. Is the degeneracy fully lifted? Well, I would say no, it's not fully lifted, because if you stand up in one direction, you're still symmetric around a single axis. So they're not going to fully lift all the degeneracies, but I don't know what the degeneracy of the nth eigenvalue is going to be. All right, so that's 8. Let's do number 9. You guys see this? I think you guys can read this. It's okay. I'm reading it out loud anyway, so I guess reading it isn't super important. Problem set 9. Coulomb potential superposition states. Let psi and Lm r denote the properly normalized energy eigenfunctions of the Coulomb potential principal quantum number and angular momentum quantum numbers L and M. Consider an electron in the state. Okay. Find the normalization constant C. Its expectation value. Write down this at some later time. T. I think so. These are the energy eigenfunctions here. So this is going to be, we're just going to add in a phase here. No. Like there's going to be an E, there's going to be a phase terms here. All right. This is going to be a little challenging. 2, where does a weakly bound electron live? Consider an electron trapped in a Coulomb potential in the state corresponding to the maximum orbital angular momentum L equals n minus 1. Show that the expectation value of, are we looking at spherical coordinates? I don't see a vector on here, so I'm assuming this r is just the radius. Show that the expectation value of the radius is equal to n plus 1/2 r naught, and that r squared is equal to r naught. So I did this. Where are we getting r naught from? Okay. Problem set 9 is going to be hard, I think. Use the above results show for large values of n and l, r squared is an r naught n squared. That is, show for large values of n, the electron is well localized near the surface of a sphere of radius n squared of r and has energy which is the same as that of a classical electron in a circular orbit of the same radius. What can you say about the size of a weakly bound state of hydrogen? Is this a quirk of hydrogen, or is it generally true of weakly bound states? I'm not sure. 3, mighty fine structure. Estimate the leading correction to the energy eigenvalues of hydrogen due to relativistic corrections to electron energy. So this is this momentum to the 4th operator here. Use your results to make a diagram of the energies N1, 2, and 3 states both before and after, including this fine structure correction. I'll have to go back over those notes, but this is adding up to the fourth term. Separates out the degeneracies. 4. Short answer. Coulomb is not hydrogen. Answer each part with no more than one short sentence and no more than one equation. By hydrogen, let's agree to understand a simple model of an electron in the Coulomb potential, which we studied in the lecture so far. Consider a hydrogen atom in its 100 ground state. Is the electron in motion? No. I would say no. Why doesn't a hydrogen atom in its ground state radiate? It's not moving. Consider a hydrogen atom in its excited state. Is the electron in motion? Why doesn't a hydrogen in this excited state radiate? Experimentally, if we excite a physical hydrogen atom from this to this, it will relatively quickly decay down to the ground state. How much angular momentum would our atom of hydrogen emit in the process? What wavelength will the resulting radiation have? How does this compare to the Rydberg-Ritz formula? Experimentally, excited atoms radiate and decay to lower energy states. However, in A to D above, you correctly argued that 804 mole of hydrogen does not radiate. There is apparently a contradiction between your correct argument and the experimental fact that atom decays to a lower energy state. What is missing in our model? In a more realistic model in which such decay is possible, can the energy operator possibly be Hermitian? No, because there's photons going off. But it's not clear what's missing in the model that would cause the higher excited energy states to decay downward. 5. Lab exercise 2, multiple wells. All right, I've got to get this Java installed. All right. Run this simulation called band structure and use it to answer the following questions. Note that the numbers produced by this simulation are correct for a particle of mass electron equals this, the electron mass. You're strongly encouraged to work in groups. Oh no. I'm going to be a group of 1 right now. This is 40 points. 40 points. Wow. I don't know whether I'm going to do this one, guys. I'm going to be in a group of 1 this whole time. All right. Set the potential to 1 square well and height 18.2. And then let's verify their 3 bound state. N equals 2. This is where we're getting into the periodic wells. So we're looking at crystals and stuff. And this is the experimentation for that. All right, and we got one more here. 0-point energy in a lattice. Consider a particle mass m in a lattice of delta function barriers of a dimensionless strength G0 greater than 1, lattice spacing L, and total length D much greater than L. Estimate the ground state energy and compare it to that of a particle confined to a box of width D. Okay. Blinded by science. Diamond with a band gap of 5.5 electron volts is a spectacular insulator. At room temperature, diamond sports roughly 10 to the negative 44 times fewer electrons in its conduction band than silicon band gap. Diamond is also famously inexpensively translucent. What is the minimum frequency to which diamond is opaque? What kind of radiation is this? Curiously, some diamonds are tinted blue. Can you come up with a mechanism that would explain this observation? Impurities? I don't know. The world is full of fermions. Is there a composite object such as the hydrogen atom will behave as a boson or a fermion? Well, fermion, obviously. Argue in general that objects containing an even odd number of fermions will behave as bosons, fermions. Oh, interesting. Objects containing an even odd number of fermions. Okay. This has to do with this identical particles thing. Identical particles and spooky correlations. Consider two variables, x1 and x2. A natural question is whether knowledge of one variable is predictive of the second variable. Such predictivity is called a correlation. In terms of an expectation value, as a natural measure, the correlation of two variables is the correlator, x minus the expectation of x naught times x2 minus the expectation of x2. All right. Suppose we carefully arrange two particles in a harmonic oscillator potential such that one is in the ground state and one is in the first excited state. The following are three wave functions in which our two particles may find ourselves, corresponding to distinguishable, bosonic, and fermionic antisymmetric particles. All right, this is from the class. Verify that the expectation is 0 in all three cases. Compute the mean square distance in each of these states and verify that the particles in various states experience different forces. Explain why. If not, what is causing the particles to attract or repel? So this is this idea of bosons like photons and force-carrying particles, that they like to be in the same state, hence lasers, and that fermions have the Pauli exclusion principle and they don't like to be in the same state, hence the reason why my hand doesn't go through the table right now when I put on it. So, all right. Suppose your lab partner places 9 identical bosons of mass mu in an infinite square well of width L, cooling them to the lowest allowed energy eigenstate. What is the wave function of this lowest energy eigenstate in terms of the single particle states? What is its energy? What is the minimum energy you must add to the system to excite it to the next? Fermions. Oh boy. All right. This was something that I struggled with, I think, in the class, this whole identical. It just didn't seem to me to be a physical argument. It just seemed to me to be like, you know, by definition, you can do this. It just doesn't seem like that would imply a physical property. So I don't think I understand the argument fully yet to get why that's true. 5, the meaning of the crystal momentum. This is Q. All right. Suppose a force F, use elementary physics like conservation of energy and the fact that you can show that this is equal to this. Okay. Let's dig deeper. If h bar q is not the momentum of the electron, whose momentum is it? Suppose that this momentum is really the momentum of some particle-like object in our system. Let's call it the quasi-particle, some effective quasi-particle mass. Show that are they known electrons? If not, what are they? This is related to the ping pong ball experiment he did. Basically, that when you're moving a ping pong ball underwater, because it's buoyant, you would expect it to just shoot up really fast, but it doesn't. But that's because it's dragging the water along with it. So my guess is that what this is saying is it's maybe dragging along some. Who knows? I don't know what it's dragging along in this picture, but it's definitely not the electron or an electron on its own. The group velocity and effective mass is considered our lattice of delta functions, group velocity, mass. What happens to this near the top of each band? What about in the middle of the band? Consider an electron at the bottom of an otherwise unoccupied band. Now accelerate with uniform electric field E. Show that the crystal momentum increases linearly in time. Qualitatively, what will happen in the Q for the conservation of momentum, or the fact that metals conduct in response to an applied electromagnetic force. Okay. They talked about this in the class. See, one of the things that I didn't get in the class when they were doing these bands is the idea that like the band gets filled and then you have to put something in a higher band. I never understood why, if you've got all these different energy eigenstates, like a continuous range of energy eigenstates, I mean, why can't you just have two in one band? Why is there only one per band? I mean, maybe that's related to the fermion thing. Maybe that's related to this stuff up here. That didn't jump out at me as being obvious in the class, but they kind of said it like it was obvious. All right. Okay, we just did this. All right. Transmission, reflection, and band gaps in one dimension. Band structure is intimately connected to scattering. As discussed in the lecture, the existence of gaps is a consequence of the destructive interference between waves reflected from a distant well in the lattice. This problem will further develop the connection between scattering and band structure in one dimension by using the transmission and reflection coefficients of a single isolated potential to drive the band structure of a lattice of identical such potentials. Ooh, okay, boy. All right. This is gonna, problem set 10 is gonna be hard. Consider an arbitrary but reasonable potential barrier described by a symmetric function v of x, 0 outside a region of width L, centered on the origin, and varies in some simple but non-trivial way between this and this. Now send a beam of particles of mass m and energy this towards the barrier from the left, outside the barrier where the potential vanishes. Okay. Similarly, sending particles in from the right at the same energy E gives this. A general energy eigenfunction, energy E, can be then expressed as a superposition of these two scattering solutions. Now consider a lattice of such barriers. Bloch's theorem. That's how you spell it. He said it in the lecture, and I felt weird writing it down because I was like, is it B-L-O-C-K? Bloch's theorem says that we can find energy eigenstates which satisfy the periodicity condition. This also implies this. Meanwhile, from our study of these single well solutions above, we know that requiring that the form of the energy eigenfunction eigenstate satisfies the Bloch periodicity conditions. All right. Show that condition on Q and E together with the definition of the scattering phase above leads to this. The band structure is thus completely determined by the transmission probability and phase shift. So now the reason scattering information is so valuable, it encodes a great deal more than just how likely is it I'll tunnel through this wall. B, for Vx, a general potential, explain why there are no solutions to the equation derived in part A in the regions this for any integer n. These are the gaps. What role does the scattering phase play in the band structure? Suppose the barriers in V of x are very weak. What does this imply about TR? Show them the limit. The energy gaps are very narrow. The width of the gap. So this is just basically when you change the wells or barriers to constant, we should retrieve the free particle condition in the limit. Suppose the barriers in Vx are very strong. What does this imply about Tr and psi? Show that in this limit, the allowed energy bands are very narrow. So the band distance is proportional to this. What are the allowed bands centered? Where are the allowed bands centered in this limit? Sketch E of Q. For V of X, a delta function barrier with G naught greater than 0, use previous results to show that use this result to reproduce the result derived from the periodic array of delta function barriers. Verify the results you found for a general potential and parts be both obtained for the specific potential. Now consider a lattice of attractive delta functions. Again, plot this. What has happened to the single bound state of the isolated attractive delta function? That is a good question. I have no idea. Optional. Ooh, well, we'll see if we have time. Standing waves at the band edges. Aside, the appearance of gaps in the spectrum of energy eigenvalues is a striking feature of the periodic potential. As we have seen, the widths of these gaps decrease to 0 as the strength of the barriers between the wells vanishes. Thus, the state at the top of one band and the state at the bottom of the next band become degenerate as the potential is turned off. Conversely, then, the periodic potential must break a degeneracy among two free particle states, with one state becoming a higher energy than the other as the potential is turned on. With one state becoming a higher energy than the other as the potential is turned on. In this problem, we will explore this process by studying the states at the band edges. Consider the lattice of delta functions, okay? States at the edges of the allowed bands at this, y. Start by thinking about the qualitative shape of the wave functions, the band edges. If we could turn off the potential, we could find two degenerate free particle states, both of which are periodic. Now imagine gradually turning on the potential. It's a delta potential due to other degenerate wave functions. Make a qualitative sketch. Which of the two states becomes the top band, which becomes the bottom of a band? And that is problem set 10. I'm trying to think of what I want to look at the midterms. I don't think so. I think it's probably best to just get going. So let's go and see where I left off. Yeah, I left off in problem set 5 because I think that's where I should pick back up. So let's go find problem set 5 here. So let me jump over. I think I want to switch the view to this. Oh, no, wrong one. Thanks, Tapas. No, this is the wrong one. How do I switch this one to? Let me add a browser here. Screen share. Actually, I do want this one. Okay. Let me try loading up one of the problem sets. Problem set 5. me crop this. All right. We're problem set 5. Okay, so I've gone through all the remaining problems. I think, do I have volume coming from here? Let me just do this one off. All right, so I've gone through the remaining problem sets. There's some stuff that seems like I feel like I've got a good handle on it. Some of it I'm just gonna have to see when I do the math. Some things that are like, okay, that seems obvious, but then how do you prove it? Problem set 5. This was a big mess right here. I remember this just being a lot of trigonometry and me screwing it up. We did questions 3, and then I think we did part C, D, do later. So where was this? This was question what? 3. We go to problem set 5. This was this harmonic oscillator potential, and then operators for the harmonic oscillator. Okay. So I think maybe I want to just go and start with because I think I stopped doing this one. So I'm just going to put these notes to the side right now. I've got I'm on my second notebook already. And I think I'm just going to work on finishing problem set 5 first. I want to see if I can just redo 3. I think I'm just going to start from the top on 3. Just put away my old notes. Don't look at the answer. Just see if I can redo 3. I may go back and even just reattempt some of these old questions here. And then let's get the solution sets in the other window here. Just before I get started, I'm just going to quickly use the washroom. All right. Let's go through this again. Wait, I got to make sure that I'm not... Okay, this is my window. I got to stay in here, otherwise you're not going to be able to see. So, harmonic oscillator potential, all right, as an initial wave function of this. the normalized eigenstates for the harmonic oscillator. Write down this. You may leave the expression in terms of phi 0, phi 1. So let me just jot this down. So we have psi of x 0 is equal to 1 over root 2 plus I 1. Now we want to have, we need to have psi x and t. Now these are energy eigenstates, so it should just be up to an overall phase, no? So it should be 1 over root 2 e to the what would it be? E to the I. I don't know what the phases of these things. This is 1. Now, would it not be something like that? I think we actually need to know what these are. I just put them in this general form. Well, let's look at the Schrodinger equation was going to be what we've got. Let's get our Schrodinger equation here. So we've got this is 1/2 m omega squared x squared times and this is going to be also equal to the time derivative. No? Where's the function for relating time derivative to? Here we go. So this is This is IH bar dt. But I want IX and t. Where do we have our... What is the form of these energy eigenfunctions? Because I think maybe that's what I want. How do I get this phase information? I'm going to make a note here for forms of 5. Okay, it's right here. So we've got this e to the alpha t. I'm just going to cross this out. These are not just e, these are the energies. Two. Are divided by 2. This is 1, which is for the first excitation is 3 omega naught t. So this is our answer for this question, and then which I'm pulling from my solution, so I'm not solving that, but I forgot that this energy is up here. Just gonna make a note of that. Okay, and this is A. Let's tackle B. Find the expectation value x as a function of time. Notice it oscillates with time. What is the amplitude of the oscillation? What is the angular frequency? All right. Well, this is, hold on a second, this is psi of x and t. I actually need to also have psi squared x of t. this is going to be 1/2. And we're going to have so I'm just going to put these like this. Complex conjugates of these are going to be e to the I omega t 2 plus I. So this is going to be minus I and this is what we have up here, e to the 2 plus so we multiply these two guys together and we're going to get 1/2 R. These two faces are going to cancel, so we're going to get these cross terms, which is going to be this plus this, be I. It should be purely real though, so where am I screwing up? Minus 3, 1/2 minus 3/2. It's going to be what? Minus omega t. So this seems wrong on its face because I've got these imaginary terms here. So what am I doing wrong? Let's look at what I wrote down for the answer here. Oh, take advantage of all real energy eigenstates. So I did do that right, but I got this garbage over here. So somehow they converted it. I'm just going to write here. Somehow they converted this into that. But how do we get there? Take advantage of all real energy eigenstates. So let's look at the answer here. Oh, we're on 3. Okay. No, this is E over H bar. So I got to this line, and then they substitute out this. So how do we get that? How do we get these to be real? Ah, okay, so here, I'm going to write that down in pen. So if we get that, we would have 1/2. Okay. So how are we getting this here? Well, so let's expand this over here. We're going to have times, let's say this is cosine omega 0 t plus I sine. But this is a negative, so we're going to have negative, negative, cosine, negative t. Guess I can just put it like this. Sine. Cosine minus omega t plus I sine t. So cosine is even. So we have I sine is equal to negative I sine omega t. So we get a factor of 2. And then the i's cancel with the minus. So this becomes 1/2 Okay, so that is our solution to A. Now let's go on to B. Find the expectation value. So do I want to just calculate it out the normal way, or is there some trick that I can find with this? Well, I know it's going to be varying with this sine omega t. Do I want to calculate it all out? No, let's just go through it for practice, the whole step. Okay. So x and we're going to have the same thing that we had last time, but there's going to be an x in the middle. So let's just pretend if we had an x here on each of these, it would mean that there would be an x term here. I think we would just multiply it all out, so there would just be an x next to all of these. X is going to just carry through. So we're just going to have x of, let's put it this way, sine x, which is going to be just what we have already. So what do we know about this? Well, we can separate these out. This, because we know these are state symmetrical states. These two are going to be 0 and expectation. And we can separate them out. So then it's going to be we can get rid of this 2 too. It's going to be x psi 0 x psi 1 x sine omega naught t x. Well, this looks generically messy. Can we integrate by parts here? If we were to integrate by parts, what would we take as the u? I want to pull this out in front. I'm just integrating by parts again. uv is equal to u prime, like that, right? And then we could try doing integration by parts. See if that goes anywhere. So let's take x to be u and this to be v in our thing. So we're going to go no, that's not going to work, I don't think. No. I don't think that's going to work because we're going to have to evaluate at the end. There's some trick I'm missing. All right, let's see what the trick is. We can pull out the sine omega t. Oh, this is actually tricky. What is the solution? Okay, so we're going to use the form of this. So let me just write down what I have in a different form. Sine not t. And so let's put in the precise forms here. X. What do we want? X times, and this is m not. And this is going to be x root 2 a. So let's see if I can solve a bit more of it now. All right. All right. This is going to be, well, let's just add these guys up. So we're going to have and I'm going to apply. Let's change this to square root here. We're going to have x squared root 2 over a times e to the x squared over a squared dx. So this is our x squared multiplied by a Gaussian here. So this isn't obvious, so it's going to solve it. Guess I can bring these factors out. So we're going to have root 2m not pi a by this integral what was our A? A was defined as what? So let's put that over here. A equal to square root of h bar over omega. And then what's this horrible integral going to be? I'm just going to put this here. Well, we know that this should be 0, right? Because we have x squared this is going to turn back into a Gaussian. I want to say this is if we had a squared and then we took the derivative, what would happen when we would take this would drop down and then we would have this, but we'd have this subleading term. I don't in general know that. Oh, okay. So they decided to do it a little differently. Let me just write that out. Let's do, this is x over a squared. I just don't know how to take that integral. U squared. Thanks, Katya. What the heck is going on here? We've got a squared. Where did we get the other a from? I guess the idea is that we're multiplying everything by A. So we're saying let X be equal to so we did change of variables here and moved out the A. So said let U equal to I have no idea how they got this to. Because they got pi by 2. Must just be a fact. Yeah. Yeah. H bar over 2 m omega naught sine omega naught t. All right. Well, that's unfortunate. I find that too difficult. Let's go forward and try C. Find the expectation value, P as a function of time. So let's just do the same thing we did before. They were saying also we could have done it with the angular frequency. Wait, hold on a second. The amplitude of the oscillation. This is amplitude. And this is angular frequency. All right. Expectation of momentum. Function of time. Let's go. Same thing. Let's just look at this thing because there's a way of doing that question with the A operator. So let's see if I can just see if I can try it with that. So let's remind ourselves what the A operator is. It should be, what is it? P squared over P naught squared. Plus, minus, plus. Should have got the notes over here. Oh, oops. X hat over X naught plus I P hat over P naught. And let me just write down the A bar was minus, right? I think that's the A adjoint. Okay, I'm also going to make a note to print off formula sheets because I'm wasting a lot of time looking back and forth here. All right. I think it's the minus. Yeah, it's minus. Yeah. Okay. So how can we find this with this A operator? Well, we know when we take A is equal to what is it? H bar omega naught. So, is there a way of doing this? What we just did with the operators. Let's back up to what we had. We had this. So if we, hold on a sec, if we take the A operator, we'd lower the 0 to 0 and that to 1. Just make it all equal to 0 though, right? Yeah, it's not clear to me at all how you solve this with operators. Let's see what it says in the notes here. Oh, okay. So what this is saying, just switch to pen. This is saying if we expressed x in terms of h, it would be 2 omega. How do we get to this? Problem 4e. Oh, we haven't done problem 4 yet. This is problem 3. Okay, so I'll have to work on that problem 4. But let's just try to work with this form and understand what we could do here. So if we're trying to do the expectation of, well, this is going to just come out of plus, h. I guess it doesn't matter, h. Of psi complex conjugates. dx, yeah. So if we wanted to go through this, this is going to be, what is our function? Well, we're going to get this is equal to equal to 5, 0. So it's going to be 5, 0. Guess we need the normalization. I guess I can just pull it over here because it's going to be everywhere. We need 5, 0 star, but we can make that equal to the real one. What did I write down here? I guess we can just make this like this because these are equivalent. Then this is minus I 1 e to the plus, no, this is e to the I 3 omega 2. And then all of this is times, well, the A operator, phi is going to lower it by 1. So by linearity, we can do the lowering operator on the 0 is going to give 0. The lowering operator on the 1 is going to give plus I. Oh. Let's get rid of these phases right now. I'm going to not do it with the phases. Let's do it with root. And let's say we've got this 0. Times a bar a is I guess I need dx here. Just put the dx here. And then this is going to give us a 0. So we have 0 plus I 0 is going to give us plus phi 1. And this is going to raise this to phi 2. So plus I phi 2. Oh, don't dx twice. All right. So what are we going to get here? What we're going to get, we can guess this up, we're going to get This times this is going to be this times this is going to be this times this is going to be this is going to be I think it's going to be minus the complex. We've got plus phi 1, phi 2. So because these are all linear, we can all treat these separately. So 1 over root 2. This is just going to be 1. This is just, so I'm just going to cross these out. So this is just 1. This is just 1. And then we have what? 2. Is that not right? And then we're going to have two root 2 pi 1. So what were the forms of them? Gonna have and then this is x, what, x root 2 over a? It's x 2 over a. And this is plus. Well, now we need the second excited state. I feel like I'm going the wrong direction. All right, let's see what we got. See if I was on the right track. Okay. So they must have pulled out the... Man, I'm struggling to understand what they're doing here. They must have pulled out... So I did it with the 5s without this, but they put it in. This is also from problem 4. So I should just wait. I think this operator method, I haven't learned enough to use it. All right, let's try C. Oh, we're getting a little close. So you know what? I'm going to just use this as a moment to pause. We're back on the problem sets. Let me just switch over here. So I'm back on the problem sets. Still hard, still challenging. Now we've got more material to cover. So I'm going to try to work through my best I can through problem set 5. Let's try to finish that today. Start working on 6. It's Friday today, so I'm a little bit ahead of schedule. I was thinking I might still be doing lectures today, but I'm a little bit ahead of schedule on the coverage front, which is good because I'm going to need every hour I'm going to need to work on problems if I'm going to get this handled by the end of the month. So I'm going to keep working on it. I'm going to be back here on 2 p.m., try to put in another 3 hours on these problem sets, relax, take some time off on the weekend, clear my head, and then back on problem sets again. My hope, if I was to be really optimistic, is that we're doing about 1 problem set-ish a day. That seemed to be roughly the pace that we were going at earlier. I would expect it was a little bit faster than 1 problem set a day. So I'm imagining that I'm probably looking at finishing maybe Thursday. And so if I look at the calendar, if I were able to finish around Thursday, that would give me another 8 days to work on the material. And I mean, there's still a lot to do. So as I've said, there is definitely a possibility here. This class is too hard for a month time, but I'm going to keep working on it. I've always found that if you just keep on with a challenging goal, so even if it doesn't always work out, if you keep on with a challenging goal, that's going to maintain the momentum a lot better. So if I say to myself, oh no, this is too hard, let's pick something easier for a target, I'm not going to be as motivated to work hard for this month. And my goal was to get as far as I could in this month. So I want to still keep the same goal. Now, if at on the 30th or whenever I'm done, if I'm working on trying to do the exam and it's like, no, it's not happening, then it's not happening. And I put in a lot of work and I didn't get as far as I wanted to go. But I'm still going to get a lot further if I do it this approach than if I just sort of say, oh no, this is too hard, or I'm going to give up or something like that. So I'm still maintaining hope. I do know that this is super challenging right now for me, and there's a lot of stuff in the problem sets where they're whipping things around, which is just going over my head a little bit. But I'm going to stick to it. I'm going to keep trying. I'm going to keep working on it. Some people have been asking me, how do you maintain motivation? How do you keep the focus for studying? I think a big part of it is that I know that this is going to be very challenging. So I know that if I don't put in the work, if I miss, let's say, a day or two, there is a chance that I won't be able to pass it. And that pressure, I think, creates a lot of the motivation to go forward. And so that's also the reason I pick these kind of benchmarks of passing the exams or doing this rather than just something more vague and abstract. I do think that this external incentive isn't the only reason that motivates me. After all, to put oneself in a situation where you feel that pressure, you have to feel like the overarching goal is worthwhile enough. And so for me, I like to focus on two types of motivation for these types. And one of them is about the intrinsic topic itself. So when I'm tackling problems like this, one of the reasons is I really want to understand quantum mechanics. I want it to be something that I get in a way that I don't quite right now. I sort of get it, but I haven't gotten that to that rigor that I'd really like to get. So there is that kind of topic motivation. But then there's also a motivation from just the wanting to set a challenge and stick through it. So I can even think of those dual motivations playing a big role when I was doing the MIT challenge or my other ultra learning projects, is that yes, there was a strong motivation to learn computer science, but I don't know whether that motivation was enough on its own to sustain the project. Instead, it was coming up with the idea of the challenge, coming up with the idea of pushing yourself to that limit and holding yourself accountable. So for the same reason that people who, let's say, run marathons are not motivated just because they wanted to cover 42 kilometers, so they wanted to cover that distance. They were motivated because they wanted to challenge themselves and see that challenge through. I am also like that. I wouldn't say that I'm necessarily like a marathon runner in this sense, but I'm also like that in that part of my motivation is coming from wanting to study quantum physics, and that was the reason for developing the project in the first place. That was the reason for picking this subject and deciding on this challenge. But then when I'm in it, in the thick of it, that's often not enough motivation to stay focused on this. So just, oh, I want to understand quantum physics is not enough for me to study hard on this for, 6 hours a day, day in, day out, especially when I'm facing frustrations like you can clearly see I'm facing. Rather, it is, I've set this challenge for myself and I want to see how far I can push myself. So there's a personal interest in seeing how far I can go, irrespective of the actual merit of the goal at the end of the day. And what I've found from doing these time and time again is even the ones that don't work out. So, I've had some successes, but I've also had some times where I try a project and it doesn't work out the way that I want it to. It could be a situation like this one where I just don't have enough time. I wanted to get somewhere high and it's actually a little bit harder than that. Or it could also be just the way I planned the goal isn't really getting me in the direction I wanted to reach. But even in those goals, the wanting to stick to the kind of pre-committed plan that you have, the wanting to stick to that intensity to push yourself as far as you can go, that's a big motivation for the challenge for me. And when I step back and I finish those at the end, there is not only a feeling of satisfaction that you've gotten something, that you understand something that was really hard for you to understand in the beginning, but there's also a satisfaction in that you set some target for yourself, you set some challenge for yourself, and you stuck with it. So I think the ultra learning projects that I try to take on really kind of fuse both those motivations. So if you're thinking about this and you're thinking, there's no way I could study for, 6 hours straight, day in, day out, I think you'd be surprised what you could do if you saw it in that way. If you saw it in, I want to challenge not only myself to accomplish some outside goal, not even just to accomplish some intrinsic interest in the subject, but in order to challenge yourself and see how far you can push yourself, how far you can handle frustration, how far you can do without giving up. At the end of the day, or at the end of the month rather, I might not be successful at this goal, but I want to be satisfied myself that I didn't hold anything back, that I went as far as I could, I pushed myself as hard as I could within this constraint. Now, it may be a question asked, why 1 month constraint in the first place? And the reason why, in my opinion, is just that your time is always limited. I like to put these 1 month constraints because it is a challenging constraint. It is going to push me to study. If I just said, well, I'm going to learn it over the next year, I would not open the problem sets probably. I would procrastinate, waste time, because there wouldn't be that pressure. There wouldn't be that urgency. And so for this challenge, there's a good chance I will fail after a month. I won't be able to reach the benchmark I've set. Definitely the problem sets are tough going. This is harder than any of the classes I did in the MIT challenge in terms of the problem set difficulty. And so because of that, it may just be that I'm not able to do it in a month. But in the same sense, that month, I will have gotten more in that month than I could have with any other approach. And so after that month is done, I can then decide what I want to do after that, whether I want to go through 804 and deepen it, whether I want to try to go up to 805, 806, keep learning quantum physics, whether I want to set up some different kind of project, whether I want to go push the project into overtime. I can choose those things once that deadline's been hit. And I mean, that's kind of how I worked when I was doing, let's say, learning Chinese, is that I learned as much as I could in that 3-month period. But I certainly wasn't fluent. I certainly wasn't in the level where my Chinese was perfect, but I had accomplished enough. I had achieved enough momentum that it was like, okay, I really want to keep doing this. I really enjoy this. I really want to keep learning. And so I learned more characters, learned to read, and now this is just sort of part of my daily life. So I don't know what role quantum physics is going to play in this. I don't know whether this is going to be something that, you know, at 804 was enough, or this understanding, as flawed as it was enough. I don't know. But I know that I'm going to keep working on it. And at the end of the month, that's going to be my stopping point to decide where I want to go next. I'm still hopeful that I can overcome my weaknesses and pass the exam. Part of me has my kind of fingers crossed that the exams tend to be a little easier than the problem sets, because the problem sets, the understanding is that you're asking questions, you're having help in recitations, that you're talking to your classmates. They're supposed to be harder, and I'm missing a lot of that extra support. Whereas the exam is more like how I'm actually studying, where I'm by myself. I don't have, you know, any input. The difference as well also is that I am using feedback. So I'm getting a little bit of the answer and then going further. MIT students don't generally have that. Although I think that because you're collaborating or working together on problem sets, it does help a little bit. So I don't know. I'm thinking that the exams might be a little bit easier. And so if I work really hard on these problem sets and they're still hard problem sets, I might get a bit of compensating factor from the from doing the exams being a little bit easier. But at the end of the day, I'm just going to keep working on it. It's 11 right now, so I'm going to take a little break, and then I'm going to be back at 2. Just keep working on the problem sets. That's probably all I'm going to be doing for the next 4 or 5 days. I might intersperse some Feynman techniques. I might intersperse going back and doing some lectures here. I do think I want to get through all the problem sets. So again, my spiral metaphor that I've been repeating this whole time, that some people just view it as like, okay, we do 1, we do 2, we do 3. I like the spiral. I like going through the material, having more than one pass, not covering it more than one time, but deepening your understanding in layers. And I think part of the reason is that you get that holistic picture. So sometimes if you really, it's hard to master something without seeing the implication of it somewhere later. So it's hard to see, for instance, this raising and lowering operator until, oh, you also see it for angular momentum. And so you're like, oh, this is a pattern. Keep that in mind. And so I'm wanting to maintain that kind of holistic perspective. But at the same time, I think it's also good to just step back and take stock and work on things from the big picture, from working on individual components. And it means you have to do each thing at a time, but it does mean that I'm probably going to, my new goal, just as it was to get through all the lectures, is to get through all the problem sets first pass. And then I might decide whether I want to do second pass of the same problem sets to try to see, now that I've gone through them all there, can I answer them without looking at the answers now? Or do I want to go and do Feynman techniques? Do I want to do some working on things first pass? Do I want to work on some midterms without solutions? Do I want to try to trivially change the form of the questions, see if I can answer in a different way? It's a little hard with these problems because they're not just like insert numbers and calculate. They tend to be kind of deep questions, which are hard to make a lot of variance of. But yeah, I'm going to work on that. And I will be back here at 2 p.m. All right.